Okay, here's another conservation of mechanical energy problem, and this is a good one. This is actually a very simple problem. It just takes a little bit of time to understand what exactly is happening physically. So imagine that we take this bob, and in case you haven't heard, a bob is the name for the mass at the end of a pendulum. So a pendulum consists of a string connected to a bob or a mass attached to a pivot point. That's what a pendulum is. And we pull this bob over from its resting or center position, and we pull it over like this till it makes a 65-degree angle with vertical, and then we release, right? And it swings down, and when it gets here to its center position, it hits this peg positioned 1.3 meters up from the center, from the bob. So that diverts, or it changes the pivot point. So now this part of the string stays fixed vertically, and then this thing goes flying around at an even faster speed, like that. So the bob goes like this, and then it hits and it swings around up to the top. Okay? And the new radius of its circular motion is 1.3 meters once it hits this peg. Over here, the radius of motion is 7.91. Okay, now we understand. Now, we have been asked to find the the speed of the bob at this moment when it gets to the top of its new swing, or its new circular path. So, this is a conservation of conservation of mechanical energy problem. And there are two moments in time we're going to evaluate. We always call it initial and final, but why don't we just call it A and B? Because that's just as good as initial and final. Here's moment A, and up here there's moment B. And I'm going to list the energies like this, with a chart on the side, because there's not a lot of room left in my drawing. At moment A, the only energy that this thing has is mgh, right? Ke is 0, because it's not moving, and there's no spring involved, so there's no spring energy or elastic potential energy, as it's also called. Okay, at point B, that's when it has swung down, hit the peg, and now swung back up. This is B. Here, it has gravitational potential because it's at some height. So it has mgh there. And if we want, we could distinguish these two heights, calling them A and B. And it also has kinetic energy, which is 1/2 mv squared. We don't need to call it V sub B because there's no other velocity involved or speed involved in our problem. The only speed we care about is this one, when it's at moment B. Alright then, we're well on our way to solving. You write down your conservation of mechanical energy equation, and of course, now since we don't have initial or final, we could have called it initial or final, but who cares? It's just moment A and moment B, right? Whether it's initial or final sort of depends on what interval we're considering, so just call it A and B, that's easier. So tally up all of the mechanical energies on the left for moment A. So it's 0 for the kinetic, and then we have an mgh term. And then on the right, we tally up all the energies for moment B. So what are our energies at moment B? Well, we've got the mgh, the gravitational potential, and it's B here, plus 1/2 mv squared. And of course, with so many of these mechanical energy problems, pretty much any problem without a spring, the mass cancels. So you don't need to know the mass of the bob, which is a good thing because it wasn't given. The mass better cancel. Okay, now we have to plug in the height at point A and the height at point B, which means we have to decide what our 0 point will be. What's the 0 level for the height? Now I'm going to go ahead and just tell you this is the 0 level you want to use, because it's very easy to use a little bit of geometry to figure out this height A, and we already know height B. Okay, this is not an A in any way. That rhymed. Height A, there we go. We already know height B. Height B is this, right? And if this is 1.3, Well, that's the radius of the circular path, which means this is 1.3 meters. So from here it is 1.3, from here to here is 1.3, and then from here to here is 1.3. So the height at B is 2.6 meters. Maybe I should write that down. 2.6 meters. So now we have to find the height at moment A, right? Okay then, well, at moment A, let me come to another page here, and actually I'll just do this down here. It's not so hard to find the height at point A. Imagine we have a right triangle like this, right? Kind of looks like a sail. This over here represents this, and this down here represents this, okay? So because the blue line represents the string, here's the string when it's positioned 65 degrees over, and here's the string when it's perfectly down. Well, that blue line is 7.91 meters. It doesn't look the same in my drawing because I haven't drawn it very well, but it's 7.91 over here, and it's 7.91 over here, right? That's the total length. We know that this right here is the adjacent leg of the right triangle where 65 degrees is the angle I just marked. In other words, if we were just to look at the right triangle, this is 7.91, this is 65, and this vertical leg here is adjacent. It's adjacent to the angle, which means it's 7.91 cosine 65. Okay? So if this is 7.91 cosine 65, and if the whole thing is 7.91, then this, which is the height, this is HA, right? See that? HA. The height is 7.91 minus this part, 7.91 cos 65, right? And that's a good thing to memorize. Here's how you memorize it. You say that the height is equal to L, the length of the string, minus L cos theta. That will always be true when you're looking for this height relative to the bottom of the swing, and you're given this angle. Right? So when you're given this angle, when you're given the length, and you're looking for this height relative to the bottom of the swing, right? The bottom of this swing, that height is given by this equation, L minus L cos theta. That's a good one to memorize. But we're going to use it by plugging in 7.91 minus 7.91 cos 65 right there for H sub A. Okay, so what we have is 9.81 for G. We just said that the height is 7.91 minus 7.91 cos 65. Let me make this a little bit clearer. 7.91 minus 7.91 cos 65 equals 9.81 times the height at B. Remember that was 2.6 because it's this length plus this length, and these are both 1.3, the radius, the new radius. So that's 2.6. And I'm out of room, so it's 1/2 V squared. And you solve for V. So to solve for V, you subtract this product from both sides. Then you multiply the new left side of the equation by 2. And then you square root everything to get V all by itself. And what's the answer come to? V will be, let's see, get out the trusty calculator, 9.81 times, open parentheses, 7.91 minus 7.91 cos 65, close parentheses on the whole thing, and then I hit enter. Then I want to subtract from that 9.81 times 2.6, enter. Then I multiply that answer by 2, enter, then I square root the answer, and I'm getting 6.2 meters per second as the height. That's the height when it reaches this peak.